In this video, we're going to talk about the span of a set of vectors. So to start out, suppose that we have a set of m-dimensional vectors, v1, v2, down to vn. So up until now, we've been handed an m-dimensional vector b, and then asked to find the set of vectors x that are solutions to the matrix equation ax equals b, where A has the vectors v1 through vn as its columns. In answering questions of this type, we've noticed that some choices of B will provide us with a consistent linear system, while other choices of B provide an inconsistent linear system. Naturally, this leads us to the question, for which vectors B is the linear system ax equals b consistent? To explore this question, let's start off with an example. So we'll take two two-dimensional vectors, v equals 1 minus 2, and w with entries minus 2 and 4. So for which vectors, b with entries b1 and b2, does there exist a vector, x, such that ax equals b actually has a solution? So to answer this question, we can think about setting this up as an augmented matrix. The only difference here between the problems that we've been familiar with and this new problem is instead of having numbers in the augmentation column, we have variables. But that's not so bad. Even though there are variables in the augmentation column, we can still perform the usual row operations on our augmented matrix. So let's start out by taking twice the first row and adding it to the second row. To answer the consistency question, we remember that our linear system will be consistent as long as there is not a pivot in the augmentation column. So looking at the bottom right-hand entry, which is b2 plus 2b1, this matrix represents a consistent linear system if and only if b2 plus 2b1 is equal to 0. Now we can phrase this as, say, solving for b2 in terms of b1. So going back to our original matrix equation, this gives us a constraint on the values of the two-dimensional vector b. So this tells us that b must be the vector whose entries are b1 and minus 2b1. And if we pull out the b1, we can think about this as a scalar multiple, b1 times the vector 1 minus 2, which, if we remember, is the same thing as v. So the answer to our original question for which vectors b is the matrix equation a times x is equal to b consistent, the answer is b must be a scalar multiple of the first column of our matrix. So to reflect on the geometric content of this example, let's consider what this means. So geometrically, if we interpret the left-hand side of our matrix equation as the linear combination x1 times the first column, v, plus x2 times the second column, w, is equal to b if and only if that vector b is a scalar multiple of the first column, v. This describes, in totality, all possible linear combinations of our two vectors v and w. This concept is so important that it warrants its own name. The span of the m-dimensional vectors v1, v2, down to vn is the set span of v1, v2, down to vn, which is defined to be the matrix, whose columns are v1, v2, down to vn, multiplied by x, such that x is an n-dimensional vector, which we can interpret as the set of x1, v1, plus x2, v2, plus ... plus xn, vn, such that each xi is a real number. So it's a set of all linear combinations of the v's. Now, equivalently, the span is the set of all m-dimensional vectors b, such that the system, given by the matrix whose columns are v1, v2, down to vn, multiplied by x is equal to b, is consistent. Now that we have a name for this object, let's return to our previous example. So we had two vectors, v, whose entries are 1 and minus 2, and w, whose entries are minus 2 and 4. The span of v and w is the set of all scalar multiples of v. So here we've chosen to write this as the set t times v, where t is any real number. So geometrically, the set span of vw, by its definition, describes the points in R2 we can reach from the origin by walking some number of units in the direction of v and some other number of units in the direction of w. But our solution actually tells us that we don't really need w. Really, our span of these two vectors v and w is the set of all points that we can reach by walking, say, t units in the direction of v. But of course, this shouldn't be totally unreasonable, because we can see that w actually lies in the span of v and w. So if we think back to what it means to be a scalar multiple in R2, this tells us that w actually lies on the line which is spanned by the vector v. So when we plot these two vectors, we see that they both lie on the line y equals minus 2x.